With the adoption of the Functional Safety Standard ISO 13849 Part 1, many questions have arisen regarding conformance to this standard. One tool that simplifies proof of conformance is SISTEMA. SISTEMA is a software program that is available free on the internet from IFA, a German governmental safety organization. In this video, we will step through a basic circuit, enter the circuit into SISTEMA, and give an idea of how this tool works. We will then make some modifications to that circuit to show the differences in SISTEMA to highlight some important concepts in 13849. This screenshot gives a basic overview of what SISTEMA looks like. The left-hand navigation window gives us an overview of our program, and the right-hand workspace is where we populate most of our data. The context window summarizes our circuit and products in terms of performance level, PL, probability of dangerous failure per hour, PFHD, and other key quality metrics per 13849. The message window in the lower right gives us warnings and key feedback, and the open product library is indicated at the bottom of the screen. A good place to start is with a simple, common safety function. In this example, we have some type of hazardous motion mostly surrounded by hard guarding with a single access point, just a simple gate. The safety function is that when someone opens the gate, the hazardous motion comes to a stop. This is commonly solved with an interlock circuit. In our first circuit example, we will select safety-rated products that make safety calculations very simple, just to start to give an idea of how SISTEMA works. Safety circuits typically consist of an input device, a logic device, and an output device. For the input, we will use a SensorGuard non-contact interlock circuit to monitor the gate. When the gate is closed, the SensorGuard's dual safety outputs are on. When the door opens, those safety outputs turn off. Furthermore, if the door is open, we should not be able to start the hazardous motion. For the logic device, we will use a GSR safety relay. For the output, we will use a PowerFlex 40P drive with safe torque off, commonly abbreviated STO. These components together result in the stopping of the hazardous motion when the gate is open. 13849 defines a hierarchical structure for safety circuits. By extension, we use this same structure within SISTEMA. The basic overview is called a project. Within a project, one or more safety functions exist. Each safety function is broken into multiple subsystems. A subsystem may be one safety-rated device, or it may be further broken down, for example, when we use redundant devices. In safety, it is common to have multiple channels. Also, within the subsystem exist blocks and then elements. A safety contactor would be an element. That element would make up a block, and then two of the contactor-based blocks would be used together to create an output subsystem. If we overlay this hierarchical structure onto our safety circuit, we will call our project SISTEMA example. The safety function within that project is the safe access interlock function that we have defined. The safety products we have selected are electronic devices with their own diagnostics, and as a result they can be used as complete subsystems within 13849 and SISTEMA. The SensorGuard is our input subsystem, the GSR relay is our logic subsystem, and the PowerFlex drive with safe torque off is our output subsystem. We have two red arrows connecting each to represent the dual channel wiring each device utilizes. We will base our SISTEMA project on this safety circuit. Now we will switch over to viewing SISTEMA. The basic unit in SISTEMA is a project. We will create a new project by right-clicking on Projects and selecting New. A new, unknown project will open. We select the project and then give it a name in the right-hand window. We will call the project SISTEMA Example. Now that we have created and named our project, we need to create the individual safety functions. In the left-hand window, right-click on the SISTEMA Example project and click New. In this case, the safety function is to stop the hazardous motion when the gate is opened. We will name the safety function Safe Access in the right-hand window. The next field is the type of safety function. There are some examples shown by clicking the drop-down, and we will select the safety-related stop function initiated by a safeguard. The list consists of the most common types of safety functions. However, you can also type in your own type. This is helpful because you will often find that none of the examples are a good fit for your safety function. Next, we populate the triggering event with "the safety gate is opened." The reaction is the motor is turned off and the hazardous motion stops. The safe state is the motor is off. We filled out some basic info for our safety function under the Documentation tab. Each safety function is designed to protect from some hazard. One factor in the design of a safety circuit is an understanding of how good the safety circuit needs to be. The quality of the safety circuit is primarily characterized by its probability of a dangerous failure. In order to determine the necessary performance level of a given safety circuit, we must quantify the risk. An application that is very dangerous would likely require the highest performance level, while it may be acceptable to use a lower performance level for a less dangerous application. We quantify the risk by carrying out a risk assessment. 13849 defines one risk assessment methodology, and SISTEMA references this methodology. We click on the PLR, Performance Level Required tab. By identifying the severity, the frequency of exposure, and the possibility of avoidance, we can quantify the risk. We call this PLR, Performance Level Required. In other words, if a safety circuit is utilized to protect from this risk, how good does that safety circuit need to be? The main purpose of SISTEMA is to determine the performance level of a safety circuit and confirm that it is at least as good as the performance level required of a given safety function. Note that in SISTEMA, the default PLR is PLE. For the purposes of our application, when the risk assessment was performed, it was to determine that the severity was S2, serious, the frequency of exposure was F2, frequent, but that it would be possible to avoid the hazard under specific conditions, P1. The resulting PLR is PLD. When we review the design of our safety circuit, we must make sure that it meets the requirements for performance level D. Now that we have identified the PLR of the safety function, we begin to import the design of our safety circuit into SISTEMA. Because each of our safety devices makes up a complete subsystem, we add them directly within the safety function. Rockwell Automation has published a SISTEMA library of RA safety components, simplifying the process of adding each product to a SISTEMA project. In the left-hand window, we right-click on the Safe Access Safety function and click Load from Library. Because we have already loaded the Rockwell Automation product library, we see that as one of our options. We select that library, and then we see the Rockwell Automation products populate the left-hand window. Because we open the library from the subsystem level, the library opens the list of products that can be a complete subsystem. By comparison, if we open the library from the element level, we would see the list of components typically used as elements, such as safety contactors and input devices with no built-in diagnostics, like mechanical tongue interlock switches. We select the interlock switch SensorGuard from the list of subsystems. Then we click the Load button. This switches us back to the project view, and we see the SensorGuard has been added to our project as a subsystem. Now we will add the GSR Monitoring Safety Relay. We again right-click on the Safety function and select Load from Library. This switches us over to the library view. From the list of Rockwell Automation subsystem devices, we select Monitoring Safety Relay GSR-DI. Then we click the Load Selection button. This takes us back to the project view, and we see the GSR has been added to our project. This takes us to our output subsystem, the PowerFlex drive with Safe Torque Off. We right-click on the safety function and select Load from Library. The library view opens. From the list of RA subsystems, we select AC Drive PowerFlex 40P with Safe Torque Off. We click Load Selection, and this switches us to the project view. We can see the PowerFlex drive has been added to our project. In this project, each device has its own diagnostics and makes up a complete subsystem. This makes it actually quite easy to determine the performance level of the overall circuit. You can see the calculated performance level and probability of dangerous failure per hour in the lower left-hand context window. We can also see that this circuit performance level meets the required performance level of the overall safety function. This is indicated in the context window and also shown with the green check next to the safe access function. Just for comparison, we will show what indications there would be if the circuit did not meet the required performance level. We select the safe access safety function and click on the PLR tab. We change the possibility of avoidance from P1 to P2 by clicking on the P2 checkbox. This changes the performance level required to PLE. Notice that we now get a red X next to the safety function. Furthermore, the message window in the lower right gives us a message explaining that the circuit does not meet the required performance level because one of the subsystems does not meet the PL or probability of dangerous failure requirements. By clicking on the Subsystems tab, we quickly see that the PowerFlex 40P is rated to performance level D. Since the PowerFlex is rated PLD and it is a complete subsystem, the overall circuit cannot reach PLE. As an aside, we could potentially reach PLE by adding a contactor to the output subsystem that would be wired in series with the drive. In other words, it's not that you can't use a PowerFlex 40P drive in a PLE circuit, it's just that you have to add some additional safety output devices to be able to get there. We click on the PLR tab and change the possibility of avoidance back to P1, thus changing the PLR back to PLD. We see the red error message disappears and we have a green check next to the safe access function. This circuit is easy to implement and easy to show compliance with 13849 Part 1. If we were using electromechanical devices that were not capable of self-diagnostics, it becomes more complex to show conformance to 13849. As you might expect, this also increases the complexity of our SISTEMA project. In order to show this, we will make some simple changes to our safety circuit. In our original safety circuit, we used a PowerFlex 40P drive with STO for our output subsystem. Now we will replace that drive with a pair of redundant contactors that are wired in series with the motor. Notice that we have added arrows from the contactor back to the monitoring relay. This represents the feedback circuit that enables the relay to do diagnostics on the contactors. The output subsystem now consists of two blocks. Each block has one element, a safety contactor. If we overlay the channel structure, we see that one contactor is in one channel and the other contactor is in the other channel. Both the SensoGuard and the GSR relay are dual channel devices, so they fall into both channels. Now we return to SISTEMA. Because this overall circuit is very similar to the previous example, we will copy it as a starting point. Right-click on the Safe Access Safety function and click Copy. Now right-click on the SISTEMA example project and click Paste. We can see the copied safety function in the project window. Select the second Safe Access Safety function. For clarity, let's change the name to Safe Access B. We expand this function by clicking the plus. Since we have replaced the PowerFlex drive, right-click on that subsystem and delete it. Now we will add our new output subsystem. Because this output subsystem will consist of multiple elements, we right-click on Safe Access B and select New. We will load the contactors at a lower level. Select this unknown subsystem and name it Redundant 700S Contactors. When we create this new subsystem, SISTEMA automatically creates the underlying hierarchy consisting of Channel 1 and Channel 2, an unknown block within each channel, and an unknown element within each block. We can see this by clicking the plus at each level. Now we will add the contactors as blocks. Right-click on Channel 1 and select Load from Library. Notice that this time the library view opens with the Blocks folder open. These are safety-rated components used at the block level, which is generally an indication that the device does not do its own diagnostics. We click on the BL Control Relay 700S-CFB-Mechanical from the list of components. Notice that the data on this product populates the right-hand window. We can click either Load Selection or Load and Close to populate the contactor into Channel 1. Back in the Project window, note that Channel 1 includes both our 700S contactor and the initial default unknown block. Right-click on the unknown block and delete it. As a side note, I find it works better to add the Rockwell Automation product to the channel as opposed to trying to edit the unknown block. In the project window, select the Channel 1 block Control Relay 700S. Notice that the product info from the library populates the right-hand window. Here is a place where many people get tripped up. You might try to populate details such as MTTFD at the block level, but this will cause challenges. We really want to populate this information at the element level, one more level down from blocks. SISTEMA will then automatically calculate the necessary info for each higher level from the data at the element level. Click the plus next to the block to expand it. Notice that it is already populated with the 700S contactor. Select it at the EL element level. Now we need to populate the MTTFD data. For electromechanical devices, this is calculated from the B10D manufacturer data and the number of operations, abbreviated NOP. The B10D is based on testing done by the manufacturer. The B10D represents the number of operations until 10% of the test samples fail to a dangerous state. Safe failures, for example a contactor failing to an open condition, are typically not considered for B10D. Only dangerous failures, such as the contact welding shut, are relevant. Because the lifetime of an electromechanical device is based on it mechanically wearing out, the number of operations in the actual application of the product becomes critical. The B10D is automatically populated from the Rockwell Automation product library, but if we didn't have it, we could look it up in the catalog. We are determining MTTFD values from the B10D value, so be sure that radio button is selected. Click the Calculate NOP. Let's say we anticipate this machine being used 300 days a year, 24 hours a day. Notice that this affects the MTTFD. If the machine ended up being used more often, it would be necessary to redo the calculations for all electromechanical devices. The frequency of operation also affects the NOP. SISTEMA wants this in seconds, but it would be more typical to have this number in minutes or even hours, so we may need to convert our number into seconds. For this application, let's say we anticipate the need to open the gate twice per shift, or once every 4 hours. There are 3,600 seconds per hour, so we multiply 4 hours times 3,600 seconds per hour to get a cycle time of 14,400 seconds. We type this value into the T-cycle field and then click OK. Notice that SISTEMA has calculated the MTTFD and confirmed that the T10D data is longer than the 20-year mission time. Just for the sake of comparison, let's see what happens when we change our assumptions. Click on the Calculate NOP button again. Change the cycle time from 14,400 to 10. In other words, what would happen if we wanted to access the gate via this access point every 10 seconds? Click OK. Notice that the MTTFD of the element has changed from over 10,000 years and a level of high to an MTTFD of 77.16 years. More importantly, the T10D, which is also based on the B10D and the number of operations, in other words, the effective lifetime of the product, is now 7.72 years. This is far less than the default of 20-year lifetime of the machine. The standards say that once a device's lifetime has expired, it must be returned to a like-new state. For component products, this generally means replacing the product. Clearly, it would not be preferable to require product replacement in such a short time frame, so we would really want to reconsider how this application was executed. For this particular application, it doesn't make any sense to be getting access that frequently, so we are okay for our application. But this is an important area for consideration when deploying electromechanical devices in safety systems, especially for devices with short B10D times, such as tongue interlock switches. We click on the Calculate NOP button again and change the T cycle back to 14,400 seconds and click OK. Diagnostic coverage, DC, is an important consideration in safety circuits. It is a measure of the capability of the system to detect any dangerous faults. Fault detection is important because it minimizes the risk of an accumulation of faults. If the system detects a fault, some type of functional test must be completed to confirm that that fault has been corrected, which can be as simple as cycling an e-stop to prove that a cross-channel fault has been cleared. Diagnostic coverage is the ratio of detectable dangerous faults to all dangerous faults. Safe faults are not considered in this calculation. The determination of the DC for a product is based on extensive failure modes effects analysis, FMEA. However, there is a table in 13849 Part 1, Annex E, summarizing DC estimates for various proven safety techniques. We click on the DC tab to enter a value for this element. Because this is an electromechanical device, we see that the default DC is 0. However, there is a note commenting that DC up to 99% is possible with external monitoring. We could populate the DC value directly if we knew it. Our other option is to click Select Applied Measures to evaluate DC. The drop-down box here is a bit misleading. What we actually want to do is click the Library button in the lower left part of the window. This brings up Table E1 from Annex E of 13849 Part 1. This is an output device, so scroll down the list to Output Device section all the way at the bottom. Select Direct Monitoring. In our circuit, we are monitoring a normally closed auxiliary contact that is mechanically linked to the main contacts. If the main motor contact was to weld shut, this aux contact would not be able to close. This is a well-tried safety technique and enables us to attain a diagnostic coverage of 99%. Click the Load Selection button. Now that we have loaded this data, we see that the block and element get green check marks. We are using two contactors, one in each channel. In this safety circuit, the MTTFD and DC for each 700S contactor is the same. This enables us to copy and paste. We want to capture the complete info for the whole block, so right-click on the BL, not the EL, and select Copy. Next, right-click on CH Channel 2 and click Paste. This will add an identical 700S contactor as a new block and element, and will include the MTTFD and DC that we input for channel 1. The default unknown block is still shown. Right-click and delete on that block. Now we want to confirm the channel 2 information. Select the Control Relay 700S element. Now check the information on the Documentation, MTTFD, and Diagnostic Coverage tabs. Even though we have populated all the information for the elements of both channels, we still are not quite finished with this subsystem. Notice that we have green checks by the CH, BL, and EL for each channel, but we see a red X next to the redundant 700S contactor subsystem. When we select the subsystem, we also see a warning message in the lower right. We have to provide more information to meet the requirements. With the subsystem selected, click on the Category tab on the right. We have 2 channels and a high diagnostic coverage, typical of a Category 4 architecture. If we had a lower category level, we would click on the drop-down to select it. Underneath the drop-down menu, there is a list of additional requirements to meet the selected category. We click the checkboxes next to the first 4 items to confirm that we have used basic and well-tried safety principles, that we have single fault tolerance, which is accomplished by the dual-channel circuit, and that the accumulation of faults does not lead to a loss of the safety function. Notice that the next 3 boxes are grayed out. These are marked based on information provided elsewhere. The MTTFD and DC average were calculated using the data we populated at the element level. When checking the MTTFD, you might wonder why it is 100 years, when each element was substantially longer. This is because 13849 limits the MTTFD of each channel to 100 years. As we click on the DC average tab, we see that SISTEMA has populated the DC average of 99%. Next we click on the CCF tab, which stands for Common Cause Failure. Functional safety standards require that specific, proven steps for reducing the risk of one event causing multiple faults are incorporated into the design. By clicking on the Library button, we bring up the table from 13849. Each practice is assigned a certain number of points. We must earn at least 65 points to prove that sufficient measures against CCF have been included. The GSR has built-in protection against overvoltage, overcurrent, etc., and the 700S contactor has no electronics, so we can select 3.1 under Design Application Experience option. This gives us 15 points. Unfortunately, we can only load one of these lines at a time, so we click the Load Selection button, and then we open the library again. One by one, we add measures 3.2, 4, 5, 6.1, and 6.2 to the CCF. This gives us a sum total of 65 points and therefore demonstrates sufficient measures against CCF. This completes the last requirement for this subsystem. Notice that the SB redundant 700S contactor subsystem now has a green check. The other subsystems remain unchanged, so we now have completed the circuit. Notice that the safety function SafeAccessB also now has the green check mark. In the context window in the lower left, we see that this circuit actually meets the requirements for performance level E. Because this exceeds the performance level required of PLD, this circuit is acceptable for this safety function. As you can see, the use of electronic safety devices that do their own diagnostics significantly simplifies proof of conformance as compared to using electromechanical safety devices. This is driven by the 13849 standard itself, and, by extension, SISTEMA also reflects this increased complexity. This difference is a result of the fact that intelligent safety devices have these requirements already designed into them, thus reducing engineering effort required of the machine builder safety circuit designer. This concludes this overview of the SISTEMA software that simplifies proof of conformance to the Functional Safety Standard ISO 13849 Part 1.